In this video, we're going to take a look at why the derivative of a position function describes velocity, and also why the derivative of a velocity function describes acceleration. So in calculus or physics even, you've probably heard this by now, but you might not know exactly why that's true. So we just want to take a look at that, and it has everything to do with the definitions of all these terms. So definition of the derivative is the slope of the tangent line on a curve at any specific x value. So first of all, the derivative has to do with the slope at any instant. Okay, and in applications, which is what position, velocity, and acceleration consider, we can also think about the slope as an instantaneous rate of change. So let's take a look at this position function. We're not going to go into detail right now about it. I'll have videos later that will go into detail about this relationship here. But for right now, position, it just identifies a location at a specific moment in time. So this equation, at any moment in time, you could plug in a time value, and the result of that, the function value, would be where that object exists. So if we look at this on a coordinate axes here, and we're just gonna look in the first quadrant. You know, time is our independent variable. It's our x value. So I'm just gonna put t for time here, and let's just consider time in seconds for this example. And our position is our y value, our dependent variable, and let's just consider that our position is in meters for this example. Okay, so now let's think, if I'm to take the derivative of this function, which is the slope, okay, and let's think about what the slope is going to be. The slope, we learned way back in Algebra 1 that the slope is the change in the y value compared to the change in the x value. It's a ratio, the change in y over change in x. In this application problem, which is time versus distance versus time here, what is our change in y? Our change in y is going to be a change in distance. In this case, it's meters. And our x value, our change in x, is going to be a change in seconds. So we have meters per second here, and that fits our definition of velocity. Velocity is a change in position over time. So here's our change in position. How many meters did that change? And how long did it take for that to occur? So that's why the derivative, which has to do with the slope of our position function, is velocity. Alright, so let's take it a step further here. Velocity function, let's take the derivative of this. And that's going to be 3t squared minus 30t plus 63. Again, we're not going to go into details about this right now, but we're just going to think about what the graph of this might look like. Again, we'll just look in the first quadrant here. And our x, our independent variable, is t. And again, we'll use units of seconds for this. And our y, our dependent variable, is velocity. So I'll put that on the y-axis. And our units for velocity that we came up with here were meters per second. So once again, if I'm going to consider the slope of this, the derivative of this, which is the slope, I just need to say, all right, change in y over change in x. That's what slope is. And what is our change in y? The units for that, it's going to be a change in velocity over a change in x. In this case, it's a change in time, which we're using seconds. And so that's why the derivative of the velocity is acceleration. Because what is the definition of acceleration? It's a change in velocity over time. So here we have a change in velocity over a change in time, which describes our acceleration. And that in this case would be 6t minus 30 for our expression representing that. I might also want to mention, this is nice to understand what acceleration is. It's a change in velocity over a change in time. Most of the time, though, you'll see this complex fraction simplified, and you'll see it as meters per second squared. But here's where it comes from.